is your second video for 7.4 exponential growth and decay. And this picks up with example 4. Example 5 is where we'll go back and revisit half-life. But for the moment, we're going to switch it up a little bit. So we have this situation. At the beginning of the summer, the population of a hive of bald-faced hornets is growing at a rate proportional to the population. That means that since it's growing at some rate that's proportional to the population, your dy dt is equal to some k times the original y. So that means our growth is exponential. From a population of 10 on May 1st, the number of hornets grow to 50 in 30 days. If the growth continues to follow the same model, how many days after May 1st will the population reach 100? So we need to come up with some type of relation for this, for our y here. Well, we know we're starting with 10 as our initial. And if we're growing, so if I look at my t and y, on day 0 there are 10 hornets. On day 30 there are 5 hornets. That means in 30 days, my population was times 5. So 5 is going to be my base number here. My rate constant is going to be 1 over 30 because that's the amount of time, like if, for example, if t was equal to 30, so on 30 days, then it would be 10 times 5 to the first, and that would give me my 50 that I wanted. This also works out that if I plug in 0, I'm just going to get 10 because it's 10 times 5 to the 0 power. So now it says we want to know how many days after May 1st will the population reach 100. So 100 equals 10 times 5 to the 1/30th power. If we go through and solve this equation, I'm going to divide by 10. So 10 equals 5 to the 1/30th t power. I can take the natural log of both sides. So if I take the natural log here, that's going to bring down the exponent. So 1/30th t times the natural log of 5. Those numbers don't disappear like they do if there had been an e in the problem. And so then to go through and actually solve, I'm going to divide by natural log 5, and then multiply by 30. That's going to get rid of the fraction. So your t value, and I'm actually going to write this over here on the left, is 30 times natural log 10 divided by natural log 5, which doesn't do us a whole lot of good in this case. We actually need to find the decimal here. So it's 42.920 days, so about 43 days. And you would want to state about 43 days will pass after May 1st before the population is going to reach 100. Okay, now, example 5. This goes back to our half-life example. If you recall from example 3, we stated that the time, so the half-life time, is equal to the natural log of 2 divided by some constant k. And that k is going to be different for every substance. This problem deals exclusively with carbon-14 dating. It says scientists who do this dating use 5,700 years for its half-life. We want to find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So if 10% has decayed, that means that 90% is left. You could set this up as your y sub 0 on the right and 0.9 y sub 0 on the left, but the y sub 0s are always going to divide out. So it's easiest to just put what amount you have left equal to e to the negative kt. We want to know how much time has actually passed with that. So again, this is specifically for half-life. The time that we're going to be solving for in our equation over here on the left is the time that it took for 10% to decay. So it's not actually the half-life time, but I do need to use the half-life time in order to find my constant K. So since I know 5700 is my half-life, I can plug that in over here and solve for K. So my K is actually going to equal the natural log of 2 divided by 5700. And so then I can pull that back over into this equation. So I have 0.9 equals e to the negative natural log 2 over 5700 times t. And then I have to go through and solve. So I'm going to take the natural log of both sides. So the natural log of 0.9 is equal to negative natural log of 2 over 5700 times t. We would solve this by multiplying by the reciprocal. So 5700 times negative natural log 2 times natural log of 0.9 is going to equal our t. So t is approximately equal to 866 years. So whatever sample these scientists are looking at, we can approximate that it's 866 years old. And again, this is really more like pre-calculus stuff, more so than calculus stuff, because we didn't take a derivative, we didn't take an integral. We did deal with the differential equation, so that's what ties that into our calculus. The last topic we're going to talk about in this section 7.4 is Newton's law of cooling. And Newton's law of cooling is a way to use that differential equation connection to figure out how much time could have currently passed with an object. And this is something actually that coroners can use if they come across somebody who's passed away to kind of estimate how long ago they might have passed within reason. This would be something that would probably only be valid for maybe a day or two. And there are other things that go into that. But this is one of the tools that they would have available to them. So you do have a couple of different variables here. K is still some constant, and the lowercase t is going to be a time. Capital T is going to be whatever temperature the object is at that time. So if it's an hour after the initial time, then capital T would be the temperature at that time. T sub S is going to be the surrounding temperature. So in most cases, that's going to be your room temperature. And then T sub 0 would be the initial temperature of your object at the time when T is 0. So like for a human, you would assume 98.6 or 98.0, depending on which value you want to use for that. It could be maybe you have, I know there's some questions that deal with baked potatoes coming out of an oven. So you would take the temperature of the baked potato as soon as you pull it out of the oven, or soup as soon as you remove it from the stove. Whatever that initial temperature is, that's going to be your T sub 0. So here's the example we're going to do with this. We have a hard-boiled egg at 98 degrees Celsius, very, very hot, is put in a pan under running 18 degrees Celsius water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. how much longer will it take the egg to reach 20 degrees? So our goal is to find a time, but just like with the other questions, they don't give us the value of K. We need to know the value of K in order to be able to figure out the time to reach the 20 degrees. So let's use the information that they give us. I'm going to go ahead and plug in the information that I know first off. T would be the temperature of the egg. So I'm actually going to use the 38 degrees in order to figure out what my K is. But I do know the surrounding temperature is 18. The initial temperature, let's see here. The initial temperature is 98. And then that's going to be times e to the negative kt power. So this is really the equation that I am going to be plugging the 20 in for. So I'm going to plug that 20 in for that capital T. But I can't do that until I know my K value. But I can use the 38 degrees as my capital T, the 5 minutes as my little t to solve for K. So 38 minus 18 is going to give me 20. 98 minus 18 is 80. And I'm going to make that e to the negative 5k. I would divide by 80. So I get 1/4 is equal to e to the negative 5k. We are going to solve by taking the natural log. So this is negative natural log of 4. Again, because it's natural log 1 minus natural log 4, and that's gone. And that's equal to negative 5k. So if I divide by negative 5, I get that my k is the natural log of 4 divided by 5. So that's always going to be my K value. So if I go back to the same equation, now I'm going to put in the 20. I can keep the 80 there because I know 98 minus 18, that was 80. So that's going to be e to the negative natural log of 4 over 5, and then times t. Notice, like my k wasn't negative, but the formula has a negative with the k, so that's why it looks like it goes back to a negative value. This is not something we would be able to solve on our own. This is something that you would have to put into the graphing calculator to solve. So the easiest thing to do would probably be to graph the left and the right sides. So we're going to graph to solve this. And you get t is equal to approximately 13.3 minutes. So notice it says how much longer will it take the egg to reach 20 degrees. So we had that 5 minutes initially. It's going to take 13.3 minutes to reach that, the 20 degrees that we're looking at. You do need to be careful with these types of questions, though, because if an initial amount of time has passed and they say how much longer, that can mean that you might need to subtract out that initial 5 minutes. Because, again, I wasn't looking at starting at 38, I was looking at starting at 98. And so, with this type of question, since it's 13.3 minutes from the beginning, 5 minutes had already passed. So our answer is about 8 minutes. Because notice it says how much longer. So it's going to be about 8 minutes longer. 13.3 minutes would be the total amount of time to get down to 20 degrees. But from the 38 to the 20 is only going to be about 8 minutes. So again, you do want to be careful with your wording on that. You don't want to screw something up just because you forgot to subtract out an initial amount. This is your homework assignment for this section. The first part does deal a lot with the separable differential equations. Again, that's what I want you to focus on, but we did do a few other connective topics that kind of make this a little bit more interesting. So go back, rewatch this video, rewatch the part 1 video, and reach out to me if you have any questions at all.